So, some of the students are asked questions about black body radiation. If I'm correct, that Dr. Joman was forwarding me some of this. I would appreciate if the student has, I mean, if the student want to tell. Am I audible? Am I clear?
Yes,
Yes,
yes.
yes.
Okay. So if the student want to speak again, like exactly what is the question, I'll be happy to take it. I don't know who is actually asked about black body radiation. If the person is interested exactly, I mean, I would be happy to hear the exact question that what the person is asking for. Otherwise, I have to give a very general description for black body radiation. That's a point. So I don't know who asked it. You can unmute yourself and ask your question if you have. Right. Okay. Then I will very briefly explain it. I have given you these relations in the beginning. There are a couple of terms here and there. So you can see that the general expression when I was writing the radians, okay, I plotted the density literally. Now I am plotting the density in lambda. Okay, so when Max Planck did up, am I audible?
Yes, yes, we are clear.
Thank you. Okay. Right. So it is where the Max Planck tried to define the radiation. Okay, so that's where black body comes. Actually, black body is nothing other than it's a hypothetical medium. Okay, there is nothing called black body. So there are, I mean, if I say that it very generally, there are world record of finding black body material, like for example, soot, carbon, the bone carbon. They are the best absorbers, so they can be used actually as some references. So what I'll do, so I give some background, maybe that maybe more is useful for you. That when we do some thermal emission measurement in our laboratory using infrared spectroscopy techniques, instead of absorption, I can measure emission, right? So we use actually, you take a piece of paper, okay, just take a piece of paper, you burn a candle and just put the paper on top of the candle and get the carbon soot collector on top of that. Okay, that's one way of doing. Then what happens is the soot make a thick layer of black material on the paper. Okay, then I will use it actually as an emitting source. Then I slowly heat this paper, including the carbon soot, then they try to emit radiation. Okay, so I can define my wavelength of these emissions. So simple cases that black, of course, soot doesn't, it still have thermal emission. Okay, you have to think that way. So then that's actually the best example of a black body. Okay, that's how the hypothetical value is getting some value literally for you to think about. So Max Planck, when he did it, he simply took a material in which it's complete black body, which is it's not existing, right? You understood what I mean, right? So then he connected this relation, the radiance, the radiation coming out of this. Okay, radiation here is photon. Okay, photon. It's a gas of mass. According to Max Planck, it's a gas of massless, uncharged bosonic particle. I don't know whether you're familiar with this word boson. Boson is after the name of the famous scientist S.N. Bose, right? He's from University of Calcutta. Actually, Dirac gave this name, if I'm correct, to appreciate his effort in relativity theory. So this is coming from Bose-Einstein in statistics. So boson is actually it's a particle which has integer number of spin. Okay, so that means I can put one boson over the other and build. So one example is Bose-Einstein condensation. That's where it comes from. The opposite of it is called fermions. Okay, this is very used in high energy particle physics. But anyway, whatever it is. So we consider photon as a boson, which has zero spin. Okay, simple. Okay, 0, 1, 2, 3. It goes like 0 spin, and I can just put one photon over the other. I can make a condensate if it obey the condensation rules. Okay, that's another thing. So what most important is look into thermodynamic equilibrium. I think part of your lecture also we might have dealt with this actually, what is thermodynamic equilibrium. So he basically drew an equation which connect the density to the temperature, and he basically plot this expression, and this H is called Planck constant. He derived it. Okay, so best example is tungsten lamp. Tungsten lamp is nothing other than an incandescent lamp. I remember when I was a child, we used to have this small Edison lamp, what you call this, incandescent lamp. We can use called vintage lamp. Nowadays you see some restaurants for fancy stuff. Otherwise, most of them replaced by CFL, this compact fluorescent lamp devices, or maybe more LED versions of it. So what tungsten lamp, we use it in lab, okay? We use it in lab to get a continuum. You remember I was presenting yesterday a good source of UV visible radiation. You can use a tungsten lamp. You just heat it. See, 3000 Kelvin, you get a band, 4000 shifts, and then 5000 and so forth. So its lambda maximum goes as B by T, and B is something called Lane displacement constant. I'm not getting into those complications. So you see that my radiance goes as 1/5 power of lambda. Okay, this is one relation I can tell you. This is how it comes out. And lambda maximum changes with the inverse of temperature. You can go to energy if you increase the temperature, as you can see here in this graph. So this is the spectral radiance versus wavelength, and increase the temperature, it slowly try to shift to UV. Okay, to UV visible range. And this is how you use actually. We'll have a lamp in a UV spectrometer, which will have a fixed, you give a fixed electrical power into that wire so that there is resistance and it heated up. Right? Then, for example, tungsten lamp get heated up and then try to emit light. Okay? And this is maybe enough for to read further on this. Actually, you can also use the book of Peter Bernard, Molecular Spectroscopy. This is also a fantastic book that covers actually including symmetry and selection rule and then spectroscopy. Advanced level book. We used to teach this in the master level. Okay, so it goes on like that. So please keep in mind that the basic standard or the golden rule we used to follow spectroscopy for chemistry students is from the book of Banner. Okay, so I encourage you to check it. I think the copyrights are all expired now. You'll see these free copies are available in the internet. Okay, now simplicities. Okay, great. Let me continue. So coming back to microwave spectroscopy, I explained you yesterday to define something for a spectroscopist, he need two levels, which I called as E0 and E1, right? And this difference is called spectral transition, and you define this as delta E is equal to H according to Einstein-Max Planck relation. Right? This we have seen in the last class. So when you consider a molecule or an atom, the first thing that comes into my mind is actually its three-dimensional structure. You might have seen so many videos or so many animations about how a molecule looks like, right? How a molecular behavior, how an atom looks like, how a molecular orbital looks like, and so forth. Right? So it is nothing other than a three-dimensional problem. I will be dealing with a three-dimensional problem. Right? It's a 3D problem. Any molecule, if you take into consider. So we have to consider, suppose I have a molecule A connected by another molecule B. We will be having a bond which is connecting. This we consider now as rigid. That's why come later what is a rigid rotor. And this will have a given mass MA, and this will have a MB, given mass MB, right? This is how it is. So now you think about, with us, now this is the same molecule, this can rotate, okay, this can rotate with respect to its axis or in and out of the plane. There are three possibilities. I can rotate with respect to its axis, and it can rotate within this plane of the screen, right? We think this is a screen, I can just rotate A going up, B coming down, and then it's again rotating, right? Another option is that with respect to the plane of the A perpendicular to that, my A is coming towards me and B is going away from me and then rotating. These are the three possibilities, right? These are called principal moment of inertia, or principal axis. So any body, any atoms will have these three states we call IA, IB, and IC. So this term is called the moment of inertia. Moment of inertia, classically, you might have studied in your batch in your higher secondary school. What is it? Literally, moment of inertia is actually the which is connecting the mass into the distance, right? Mass into the distance separating them, or mass to diameter. So if you take any material, like which is a sphere here, the sphere here, this is your R and it has a mass M, then your I is equal to M into R squared, right? This is one thing you have studied it. And each of these systems, so now I take this particular system, I give most of the time to students some best example, like you think about what you call, the recent Olympic medal that we got for what, shot put, right? You remember shot put to the famous Ariana boy. I forget his name anyway. So you can see that. What is it actually? So when a shot put is trying to move around, it basically will have its own defined angular momentum as well as its angular velocity, right? So I will have this expression I, moment of inertia, will be connected to the term angular momentum L divided by omega. L is the angular momentum, right? Omega is the angular velocity. You can tell me if you have studied this part, and then I can skip this. I mean, it will be easy that I can cover other things. Can you one of you tell me whether you have studied this? Moment of inertia.
Yeah, actually, I is equal to mu R square is there for.
Okay, it is there in some of the courses you have studied. So I'm starting with the classical expression I is equal to mr square, which is the moment of inertia of a spherical ball with a mass m. R is the diameter, and the same I is connected to angular momentum, where L is the angular momentum. And now L actually has a vector quantity, so it has a defined. It is quantized. It cannot occupy many values. So it will have a fixed value. Okay, that's more important. So what changes literally is the angular velocity. Okay, that means I can, so when a shot put gaze is trying to throw a shot, what you do is actually slowly acquire angular velocity by keeping the angular momentum fixed, and then slowly goes up, the moment of inertia drops and drops and drops, get the maximum energy, then throw it. Right? This is how it comes out. So you think like I am having a man sitting here, and this is like your shot put over the ball, then this is rotating. Okay, now we can think about rotating the respective plane and getting some energy, then goes out, right? Goes out. So always keep in mind that molecule can still do this. Okay, it can rotate and then it can rotate and get the maximum energy. Suppose you heat a molecule, it does the same actually in a molecular level. Okay, so you heat the system very, very high temperatures. What happens? The molecule can rotate very fast. Okay, that you understand, right? I'm considering this as rigid. Okay, and after some point, if you get that much of rotational energy, okay, I'll come to that energy of this rotor. It gets some large amount of rotational energy. Then what happens? This breaks, then separate. Okay, this is possible. Okay, so that's all about moment of inertia. You may please check it detail. Anyway, I will come to diatomic rotor. I will explain moment of inertia for diatomic rotor, where Dr. Thani has mentioned I is equal to mu r square, where mu is the reduced mass. We'll see very soon. Okay, so let us see how does the linear molecule. So what in chemistry we have this notion, right? We use some concept to teach students like how a molecule look like, how basically depend upon the symmetry. I'm not touching the symmetry part. Maybe it will be very tough as for now. But what I'm trying to show you that like class of molecule, how does it behave at least? Okay, that make more comfortable. So the first system is linear molecule. Linear molecule. I can give a very good example. Hydrogen chloride, right? It's a heteronuclear diatomic molecule, right? So hydrogen is having a very small mass, whereas chlorine is very big. So it's a heteronuclear system. I can have triatomic systems like OCS, we define double bond, right? Is carbon oxysulfide, right? This is also known, is actually a linear molecule. So I was telling you there are IA, IB, and IC available to the system, right? Where I called IA actually is a rotation on the bond axis, rotation on, around the bond axis. So I will rotate with respect to this axis is the rotation around the bond axis, where I mentioned. What will happen? How much is the moment of inertia for this system? This will be 0. IA is equal to 0 because it doesn't change, right? So that's very important. So you see that the moment of inertia is 0 because it doesn't give any change in the dipole at the end. I can simply say that way, that physically transfer to you. Okay, so whereas you can have two options, like with respect to this system, I can have a movement and how to represent in the plane of the screen. I can have a rotation possible like this. Maybe the chlorine will be fixed. It's a heavy atom, right? It will be fixed, and the hydrogen will rotate like this. Okay, somebody stop me if you want to know more. I want to ask me something. Okay, so this is where IB. This is actually end over end rotation in the plane of the end over end rotation in the plane of the screen. Right, goes like then. I have IC, which is perpendicular to the plane. Okay, which is right angles. It's again end over end rotation perpendicular to the plane or perpendicular to the screen. So here for a linear molecule, what will happen is that IB will be equivalent to IC and IA is equal to 0. This is the condition. So that makes simple. At least I will of course explain of our moment of inertia of a diatomic rotor. I will come to that in a minute, but I just give you this flavor of how HCl or OCS kind of molecule is a linear molecule. How does it look like? Now I'll go to the next system, which is a symmetrical top. I can give you example of methyl fluoride here. Methyl fluoride. So methyl group, you know that carbon here, hydrogen here, another hydrogen here. It's connected by a fluorine atom. So now you can yourself think, what are the three moment of inertia for the three coordinates? One will be on this axis, which is your principal axis, right? Because of carbon-carbon fluorine bond, right? Carbon-fluorine bond. Here, this I call IA. This will be a non-zero value here because I have a heteroatom, which is connected, of course it's a heteroatom, but it's connected to some hydrogens above and below. It gets still a non-zero value of I here. Okay, so in this there are two cases. here the basic rule is IB is equal to IC, okay, which is not equal to IA. This is how it is. Whereas IA is not equal to 0. That's for sure. This is clear when it is not equal to IA. Okay, but here there are two categories. One is called prolate symmetric, other one is oblate symmetric. Okay, prolate and oblate. So I am not going to touch it in detail, but you will see what I will be doing here. For prolate system, for example, methyl fluoride, which is a prolate system, here IB equal to IC, which will be greater than IA. I can give another cases where oblate will be IB equal to IC, which will be less than A. Can you guess? Okay, there is O here. Okay, I'm writing wrong something. Okay. So oblate and prolate. So prolate will have IB and IC. Of course, here in this case, it's a right example. It's a prolate symmetric top molecule, in which IB is equal to IC, which is always greater than IA, because IA is a small quantity, right? Which also indirectly tell you that the dipole moment of rotation around the IA principal axis is giving very less change. You remember long back, I mean not long back, yesterday class, we were plotting about the vertical, the rotational dipole change. Rotational dipole change, you remember something like that is what I plotted, right? You have a position of maybe something like this, I mean, right? And then I was showing you when it is here, like you get maximum and then goes on. This is actually the respect to principal axis. So with carbon fluorine, you have to have some dipole variation due to rotation. That's what I am saying here. So for prolate system, it's very clear that methyl fluoride, what will be the case on oblate system? Oblate system, normally IB is equal to IC, which will be greater than, which will be less than IA. I can tell you this very good example. Trichloro, boron trichloride. Boron trichloride. If people are familiar with symmetry and molecular orbitals, so symmetry and selection rules, or maybe some of you master students, I'm sure they've learned it, part of it. So this boron trichloride, it's actually a dipole zero material, right? So what happens is that in plane and out of plane will not bring a big variation in dipole. So normally IB and IC will be very small. Whereas if you take one of these axes, if you take this axis as principal axis, you will have a rotation with respect to this axis, will give you some IA value which is greater than the other. Let us maybe that's where you take it. And then we go further. I can show you the next situation. This is much familiar molecule that most of the time we discussed this in many of the classes. CH4, methane. Methane is what is a geometry of methane? It is tetrahedral, right? I can have a carbon in which 3 hydrogens sitting in the base like a pyramid, and it's coming up hydrogen here. So here, what happens here? IA will be equal to IB will be equal to IC. Okay, all these cases. So in practice, this only gives us an academic interest. So it doesn't show methane, doesn't show rotational spectrum. You know, maybe some of you know it already. Why? Because of all the direction we have a dipole moment change zero, even if it rotates, right? So it's only possible if IA and IB are all the moment of inertia in all directions are equal. Okay, so that makes things very easy. Now comes to the last class of systems. This is very detailed, discussed in Peter Bernard, a book called Peter Bernard Molecular Spectroscopy. If anybody interested, I'm writing the name Peter Bernard. Okay, molecular spectroscopy. This book is discussing the details about the selection rule and symmetries of molecule before rotation spectroscopy starts. I encourage you to read it. Whereas in the case of Anvil, it discusses very, very briefly. It shows what are the important things and it goes. Okay, so asymmetric tops, these are the class of systems which normally you see around you. Okay, any kind of organic molecule, many of the organic molecules, where IA is not equal to IB, which is not equal to IC. Okay, very good example is water. C2 is symmetry. I can tell you many examples. I'll take a very simple system. Chlorine. Okay, vinyl chloride. So there are many classes of such similar molecules in the literature. So you can check it if you are interested. So many of the class of molecule come in this. So what I will do in the given time, very quickly explaining. So we are already, time is going very fast. Since you are not much familiar about rotation, I will just bring this idea of angular momentum. So, like any other of molecular energy form, rotational energy is also a quantized state. Okay, so it can only have a definite value. I said angular momentum, right? Angular momentum L will have a definite value. Sorry. Will have a definite value. So that makes the system more interesting because then you can have quantization. We will go to Schrodinger equation slowly. I will only write the expression. What we'll see in our academic curriculum, we will teach the students to solve the Ridge-Rotor model normally. But we never goes from Cartesian to polar coordinate because it's an algebraic equation, so maybe it's too boring for you and anybody will be dealing with that to deal with. So what I will write actually the right energy of a Ridge-Rotor. That's what I will start later. So before that, I want to show you how the system for a diatomic molecule looks like. So diatomic molecule, I was just mentioning, right? Diatomic. Let's write it. Diatomic molecule. So I was just mentioning here. Take a system like A and B connected. So take a hydrogen chloride molecule. One will be small, right? I mean, I'm writing chlorine will be very large. This is your chlorine atom. Defined very generally as M1 and connected to the hydrogen by a bond. Now this bond is rigid, okay? This is one of the approximation I do. So I have M1, okay? This is M2. They are connected by a rigid bond and the distance separating them will be R0. Okay, since this is large, M in weight, right? So my center of mass will be somewhere here. This I call C. I can call CM or center of mass C, okay? Then I can have a point from this center, which is the center point of the sphere, to this. I will have R1 here. This is R2, right? So this is the concept you might have studied. I have mass M1 and mass M2, and the total length I will write R0. Sorry, R0 is equal to R1 plus R2. Okay, R0 is equal to R1 plus R2. Then I goes on, I will define, since I have to always think about the central point C and you are giving a balancing equation, M1 R1 is equal to M2 R1. So I have this first equation, I have this second equation, then I will write my moment of inertia I. Normally it is summation of I is equal to 0 to IN xi, sorry, mi r I square. Okay, this is the equation for moment of inertia of many components in the system. So I have two situations, right? So I will write my actual I equal to M1 R1 square plus M2 R2 square. Okay, so what happens is goes on, like I have one, equation 1, so I will replace M1 by, I can have M1 is equal to, from equation 2, right? This is equation 3. Okay. M1 is equal to, M1 I will write as M2 R2 by R1. Same way M2 will be equal to, right, M1 R1 by R2 coming from equation 2. So then I will have I is equal to, right, M2 R1 R2 plus M1 R1 R2. I just substitute the values of M1 here. That's all I did. Right? So this is the equation which will finally match as M1 plus M2 into, right, R1 R2. So now I will apply. I already said that M1 R1 is equal to M2 R2. Now I know that R0 is equal to R1 plus R2. So I will replace R2 by R0 minus R1. So it will be equal to M2 into R0 minus R1. So then that will again give you R1 is equal to M0 R0, M2 R0, right, M2 R0 divided by M1 plus M2, right? So this is again rewriting this time, and R2 will be equivalent to M1 R0 by M1 plus M2. So I will show finally this expression come as I is equal to M1 M2 divided by M1 plus M2 into R0 square. Okay, this will be equated as mu into R0 square. So where mu is called the effective mass and R0 is the total length. Total, this is nothing other than the bond length. Okay, so this is the way of explaining a moment of inertia of a rigid rotor very clearly, where mu is the effective mass M1 M2 divided by M1 plus M2, and R0 is the fixed bond length. Okay, this is first approximation. I assume that I am fixing the bond length. Okay, but you know in reality a bond is elastic. Okay, so if you know this much, you will be able to build up, okay, this concept very easily to any level you want. That means I will, okay, so when I okay, I have to maybe give you some more clues, like, you know, when I ask a student what is a bond and what is a band. We used to ask these questions to students when they come, right? So they have to get some flavor. What is a bond? What is a chemical bond? And what is a spectral band? What is the difference? Can some of you give me an answer to this question? Maybe that way, I don't know, like there are a lot of students here, like BSc level. If you can give me an answer, what is the difference between bond and a band? No? I think many of you doesn't. Yeah, please.
Yeah, students, please. I was again requesting some of you to answer.
It's very difficult to come out of the cocoon. Huh? So, how you understand a chemical bond? Okay, you learn about this. What is chemical bond? Because you're a BSc student, you should know it, right? I mean to say some story. Otherwise, it's too boring for you that I only explaining equations and then coming up at the end.
No, one of the difficulty is most of them are logging from their mobile phone. So they have to unmute, they have to plug in maybe some background noise.
Okay, no issue.
That is the reason.
Maybe I should tell this. Thank you, Dr. Manoj. Anyway, that's fine. I thought I always love to have an interactive discussion. Then like only one fellow is talking, which is like what you call radio speaking. Like, you know, it's better that we interact. Okay, so since I told about bond and band, let us bond and band. bond, I will normally see if a student reply me very quickly, bond is a singular and bond is a plural. That's the first answer to this question. It is more than that. Okay, so if you want to explain a chemical bond itself, will require another lecture. Okay, I was happened to listen one of the famous lecture of Rolf Hoffman. He was a Nobel laureate along with Woodward. He explained a chemical bond. You studied maybe in your first year of BSc. What is the distance between a carbon-carbon bond? Right. Some teacher might have asked you this, or maybe you have studied or might have mugged up this, right? Somehow, right? I remember it because I taught. I mean, my BSc I learned one distance between carbon-carbon bond is 1.54 angstrom. Right? Correct me if I'm wrong. 154 picometer. Right? This is given in some textbook. Right? What does it mean? What does it mean actually? So the meaning is that you are fixing the bond between the carbon length, which is fixing the R between the carbon-carbon, right? And this value is 1.54. Okay. Keep in mind, am I audible? I feel like I'm stuck. No?
No. Yeah,
okay.
you're audible.
Right. Yeah. Thank you. So historically, I also want to add this. Historically, vibrational spectroscopy, which was invented first. Okay, like infrared spectrometer was invented first. Okay, so I don't know whether I will get time to show you how rotation get coupled to vibrations and give you raw vibrational spectra. From raw vibrational spectra, people calculated R in the beginning. I want to show you this maybe at some time progress because we don't have too much of time to discuss this aspect. Anyway, we will see. So there R is defined. And R can be calculated with the limitation of the instrument. But that values is like 1.54. So of course that is very close to reality. Okay, very close to reality. According to Woodward, the Rolf Hoffman, the co-author of Woodward and Rolf, this pericyclic reaction, he wrote a beautiful book actually. When you read about it, you feel fantasy, like very nice way of explaining a chemical bond. So he said that he went back. So when somebody asked him what is a bond, how you define. So what he did, he went back to the Cambridge database, in Cambridge database they have a depository in which anybody who invent a new molecule, they deposited this molecular features or structure or details of molecular bonds, etc., calculated by XRD methods, like small X-ray diffraction methods, and deposited. And there are thousands of such databases available. Anybody can download and see it. What he did, he downloaded many of the compounds which has common carbon-carbon bonds. Then he made a histogram. Okay, then he found that carbon-carbon bond is changing from 1.3 to 1.7. And it goes like histogram goes like that. Just give a Gaussian distribution like this. And the peak of this is 1.54 angstrom. Okay. Now you understand how dynamic it is. It is very important to think this way, that what you learned, you fixed the bond. This is classical approach. I fixed the bond. Exactly we started the argument here, right? I fixed R, a given value, which is not correct. My molecule is elastic. It can occupy any value between 1.3 and 1.7 now, according to Hoffman. Then I cannot just define a chemical bond as it is. It is so dynamic in nature. That's all I want to say. So you understand a chemical bond. And if I talk about a band, what you measure in an absorption spectrum is a spectral band, which is the response of many molecule response to light, not one. Okay? I hope that is clear to you. Any spectrum, what you measure in FTIR, UV visible, or any of these spectroscopic techniques, you will see a band structure, which shows that it is a collection of spectra acquired by different number of of molecule interacting present in the system, reacting to light when it's false. Okay, that's why it's called band. Okay, another thing, when you study Raman specifically, Raman is not probing directly. You're not directly exciting. Instead, you're seeing an emission or an event happening from some pseudo states. So I can talk about molecular level information in Raman spectroscopy. That means I can connect to a bond in Raman. Okay, I hope you got the difference, and maybe if anybody asks you, you can just tell this in the sense like you will see similar questions in any of these exams, which is one of your target in the current course, right? So maybe it will be useful to you. Okay, so let me go to the next portion so that I think you feel that boring part is over, like we just defined moment of inertia, right? So let us see that now a rigid diatomic rotor, how does it behave? I was mentioning then I want to go back to solve the entire Schrodinger equation for a rigid rotor. I won't do it. I mean, you can see that it's given in some books. Uri Levin has given very nice description about how the energy of a rigid rotor look like. I will write this expression. You are familiar with this expression, I hope. E of J, which is equivalent to H square divided by E pi square I into J plus 1. This is the expression for energy of a rigid diatomic rotor. Okay, where J is equal to 0, 1, 2, etc. Okay, this is called rotational quantum number, and this rotational quantum number has definite values as 0, 1, 2, 3, etc. Okay, so I can have, so this is in joules, okay, this is normally written in joules. Right? So, I mean, in the previous class, okay, so we have time. Okay, I will go again a bit slowly so that the concept has been clear to you. So J is having values from 0, 1, 2, 3, etc. Right? It goes on like that. Right? So what we will do, like, you know, I don't know whether any of you have a chance to get to know about micro spectrometer, but you know, you keep in mind that maybe many of you are using these appliances at your home, you know, micro, you know, that you are using at your kitchen. That is working on the principle of rotational spectroscopy. I hope that it's also clear to you guys. What it does is actually it is really making the water molecule present in a material, which is a carbohydrate or a protein or whatever you're just putting inside a micro oven, and the water molecule is rotating so fast that it get a lot of energy pumped into the neighboring system and get heated up. Okay, and it dissipates thermally to the other system and you locally heating it. Okay, this is how a micro oven look like. So it's a water molecule is C2V symmetry system, which is an asymmetric top. We just discussed before. I don't have time to see. If you want to know more about it, you read about it. Okay, it's also given in Atkins, which is your Bible for physical chemistry, right? You may be already knowing. Okay, so what I will say now. I want to see many of the time micro spectroscopy will be measured in wave numbers. It is too boring, right? So if you say wave numbers, I am saying wavelength, wave number, then frequency. There are many terms in which some people met. So energy, joule, electron volt, plenty, right? You know, I can write in like many ways that given energy state. So wave number is actually a linear quantity. So you see the wavelength is not linear scale. Okay, just keep in mind. You know this is already. I'm just saying this is wave number represented by this centimeter inverse, right? Okay, so EJ, I will represent EJ instead of this capital E, which is measuring the actual energy of the system. Now this goes as EJ by H into C. You get the use of the Planck constant H here, right? You got the joules of the Planck constant H here into C. This is the speed of light. So this expression comes as H divided by 8 pi square I C in J into J plus 1. Right? This is one equation. This is two. Okay. There is another thing that we normally ask, some of these integrated PhD students in the exam. What is the difference between H and H bar? Anybody can quickly answer me. If you know it, I'll appreciate that if you can answer me. Then at least I see another voice coming. What is the difference between the Planck constant h and the reduced Planck constant h bar? Not studied it. Okay, all right. So I will.
Yeah, I think we have mostly the first years and the second years.
Okay.
Very few PG students are there. Few are there.
Okay.
So they should actually know.
Yeah, they should of course know.
Yes. Right.
Yeah. So people sometimes the idea of this is we use h as a Planck constant. This is a reduced Planck constant called as h bar, which is h by 2 pi, right? This is h by 2 pi. But I want to know where it is coming from. That we may be able to. I don't know whether you checked it. Remember I was mentioning in the first slide yesterday that I was mentioning a sine rho function where y is equal to a sine theta, right? That expression goes to omega t expression. So when you have angular momentum or angular velocity come into picture, you will have 2 pi term because it's happening on a circle. So you have always 2 pi comes in. That's make h by 2 pi. To make it simple, people put h bar. Okay, that's called reduced Planck constant. In frequency term, we always use h. I hope that clarify you. I think you should, of course, check it once again whether my clarification is not correct. You will see plenty of YouTube videos available. I mean, new generations are blessed with anything. If you want to search, you can check it on the internet. Okay, you please check it yourself and get satisfied. So I will write this expression: Ej is equal to E small letter Ej into E is equal to capital Ej by hc, and this will be written in centimeter. Does this make our life easier? Because the spectrometer works exactly in the linear scale. Okay, so this is how it works out. So it goes on. So I have this particular expression, beautifully written. We call it B. Okay, so now I will write B, which is called the rotational constant. This comes here, so I have Ej, which will be equivalent to B into J into J plus 1. B is the rotational constant, and B has a value h by 8 pi square I into C. Okay, I also so now you can think how rotational constant is important. If I calculate the rotational constant, or if I measure the rotational constant, which I will show you in the next slide, how to measure rotational constant in a spectrum. What is important? When you measure rotational constant, you come to know the moment of inertia. If you know the moment of inertia of a chemical bond, you will be able to connect to the bond length. Okay, so microspectroscopy has a unique feature. I can calculate or I can measure the bond length of a given compound very precisely. Okay, which can go up to maybe after the decimal 5 digit or 6 digit. Some of the sophisticated microspectrometer. Instead of 1.54 angstrom, you get in X-ray, you get 1.54, 1, 2, 3, 4, etc. Okay, that much precisely, which is used in astrochemistry as well as industrial applications. So you see that any rocket launch from NASA and so forth, any rovers, I mean recent rovers, they have a micro spectrometer attached to that as one of the spectrometer, which basically pick up the gases there and collect it. Okay, one important point. When a system wants to show rotational spectroscopy, it should be in the gas phase. That's another criteria or limitations of rotational spectroscopy. Especially in liquid and solid state, the rotation is arrested and the system does not show up. Okay, most of the time you will see rotational spectra in the gas phase. Okay, so that's it for the basics. What I will show you quickly is, so I was mentioning that this value B. So I also mentioned that J can assign values starting from 0, 1, 2, 3, etc. Right? It goes on like this. So when J is equal to, so we have already mentioned Ej is equal to B into J into J plus 1, right? This is the expression. If J is equal to 0, the first term will be 0. So I'm writing J values here, J is 0. This will give you 0. Okay, right? So this is my Ej. Writing very clearly, this is my Ej. And 0 gives 0 in energy, and then the first level 1 will give you 2b, right? See, when J is equal to 1, 1 into 1 plus 1, that is 2b, right? Then the next level 2, how much will come? You calculate, this is equal to 6b. That means b into 2 into 2 plus 1, that 3. 3 into 2 is 6, so 6b. Then it goes like this. Third level, this will be 12b. Fourth level, this will be 20b. Correct. Okay, so it goes on like this. This is the allowed rotational transitions. Okay, so we normally ask, this semester I asked my students to comment about when J is equal to 0, Ej is equal to 0. What does it mean? So the other way I can ask this question, you heard about uncertainty principle, right? You have studied about uncertainty principle, right? Uncertainty principle says that it's a Heisenberg showed, like when quantum mechanics comes into picture, that you cannot able to predict the energy and the position of any state equally or without any bias, right? And we say that this will go to either greater than or equal to h by 4 pi, right? Or h by 2 pi at frequency time. So in angular momentum time, h by 4 pi. In frequency terms, it will be h by 2 pi and so forth, right? This is called the uncertainty principle, right? So whether uncertainty principle is applicable here, even my energy, how can I get energy 0? So you also know that there is something called 0 point energy, which is the minimum amount of energy occupied by the state, right? So the answer to this question, the question is like this: can I have 0 point energy for a rotational state of hydrogen atom? This is a question you may see in CSIR question paper sometimes. How you justify it? Okay, so why? The answer is this: that I will have a defined angular momentum, which means that one of the value is fixed. So hence I don't simply obey the unharmonicity principle. Sorry, uncertainty principle. That means I can have a 0 value for a rotational state. Okay, so now you see I have defined this value 0, 2b, 6b, 12b, and 20b, and 32b, and so forth. It goes on like that for rotational states as it climbs. And for a transition between so for diatomic molecules, we always get value from these J is equal to 0, J is equal to 0 to 1 state. This will be 2 into P centimeter inverse, right? That you have seen here, this transition. Okay, so then what is so important here, that when J is equal to 1 to 2, the value will be 4B. You have seen it, right? This is 4B. Then it will be 6B, then this will be 8B, and so forth. Go along like that. Okay, so next one will be 30B, and so the difference will be 10B, and so forth. So general, how to say, for a transition, J is equal to J plus 1. This particular transition, I can write the energy J to J plus 1 as equivalent to B into J plus 1 into J plus 2, right, minus B j into j plus 1. This is the transition possibility, and this comes out of it 2 into b into j plus 1. Sorry, 2b into j plus 1. Okay, so you can, this will come out of in centimeter inverse. This is the transition possibilities. And I already mentioned, when you do this, you can, in Banwell it is very beautifully given. I will see this way. If I write my wave number increase in this direction, I will start from 0. This is 0. Then next is 2b. Next one is 4b, 6b, 8b, 10b. It goes on like this, right? This is how the energy levels. So keep in mind that I cannot occupy very large number of rotational states. It is not possible for me. So because it gets a lot of angular velocity and simply breaks. Okay, that is not possible. So I am not coming to that. So here what happens? So you see that very easily this gap is now 2b. So for a rigid rotor, we will expect to have a spacing like this is, I can call V bar observed spectroscopically will be 2b separated. You get 2b, 4b, 6b, 8b, 10b like that in a spectrum when you measure it. And they are for, this is for diatomic molecules. I'm saying specifically for a linear diatomic molecule. Okay? Okay, so the another thing, why I said this transition, I am not going to discuss with you about the selection rule, but I write the selection rule, which is equivalent to plus or minus 1. Delta J is equal to plus or minus 1. So J from 0 to 1 is possible, 1 to 2 is possible, 2 to 3 is possible, and 3 to 4 is possible. There is a way in which it has been extracted from the Schrodinger equation and in connection to the angular momentum. I am not discussing this, is beyond the scope of our discussion. But you have to remember delta J is plus or minus 1. Okay? Right, so that's the selection rule, and then there are a couple of good problems given. Maybe in the next step, how much time I have? Yeah, I have another half an hour. So I will quickly, I don't know, I thought of not rush too much. I thought of giving you a problem, which is intensity of spectra and Boltzmann distribution. This is another thing that normally come into picture for any cases that we discuss. So you see, I was telling you the selection rule is delta J is equal to plus or minus 1. So you can have a transition possibility from J is equal to 0 to 1, J is equal to 1 to 2, J is equal to 2 to 3, etc. Right? All these are possible. So I will apply the simple, beautiful Maxwell relation Nj by N0, which is equivalent to, right, exponential of, okay, there is a term here, exponential of minus Ej by kBt, and this is again equivalent to exponential of, okay, I have minus 10, right, minus Bhc into divided by kBt into J plus 1. Okay, so this is the expression, and here one more factor comes that I will skip again, that is called the what do you call it? The degeneracy. Okay, so this is exponential term. I'm sorry, this is exponential term. Okay, so this degeneracy term I am skipping because it is coming from the angular momentum, which is again discussed in the book of Banwell. Okay, it may take another 10 minutes to explain this, but keep in mind that if I have I can write the degeneracy term. You can have 2j plus 1 levels degenerate state available. So your L, I can call for a given angular momentum what I can call its vector quantity. So you have to see that part. I mean, if j is equal to 1, you will have okay 2 into the incremental tensor. Okay, it will be under root. Okay, that's again I think you have not discussed much this, so I will skip this. What happens here, the L value will go as under root of j into j plus 1. Okay, that will be equivalent to something around, in this case it's let me see something wrong. When j is equal to 1, it will be 1 into 2. That will be under root of 2. That's energy, okay? And the degenerate states will be, as I mentioned, 2j plus 1. That means 3. So you get 3 degenerate states and the energy will be under root of 2. And so forth. Okay, that I will not discuss, I will skip it, but what you will see when you measure, that's most important. Okay, that's most important. When you measure rotational spectrum of any molecule, you will have the Maxwell distribution as comes here. You will have this particular term, right? 2j plus 1, which is the degeneracy term. I was just mentioning this into exponential term. Exponential term will come here. Okay, that when you plot versus j, you start from 0, 1, 2, etc. up to 10, say, you will get a distribution like this. It start from 1, right? Some value, and then goes up, get some maximum and drops, and 0, it becomes 0. So these will change with respect to B, or some books you will see B bar, which is your rotational constant. Okay, if B bar is 5 centimeter, I can write 5 centimeter. B1 is 5 centimeter inverse. This spectrum will look like this, and if it increases, you will see that shifts. Okay, this is a schematic. Okay, this is B1 and this is B2, where B2 is equal to 10 centimeter inverse. So this will shift. So the rotational maximum will shift, and we also see a relation J max, which is equivalent to, there is a relation here to calculate the J max. This is under root of KBT divided by 2BHC, right? 2BHC minus half. Okay. This is also derived in the book of Peter Bernard. You can check it. It is just to differentiate the population density versus the angular moment. Rotational quantum number. You get, assuming that is, dp by dj is equal to 0, and then put up this expression. You will end up in having this particular J max calculated. So in principle, I can calculate the maximum available population of a given molecule and exactly know which particular rotational state will have maximum population density. You have to think that my J increases. You see that when my J increases, my degeneracy also increases, that this quantity increases. Even if this quantity increases, you have an exponential, the power exponential minus BHC or EJ by KB available, so that means the probability drops by slowly, right? So this compensates and you get a maximum position. That's how. This is the Maxwell distribution. You will see some typical problems in textbooks. So as it progresses, you will see also other possibilities. You can see there are some very nice experiments given in the book of Barnwell, in which there are a couple of good authors. One of the author his name is Gilliam. He has a reference. I forgot to add up the reference. It's a Journal of Chemical Physics in 1950. Okay, that book, particular journal, he basically have calculated carbon monoxide C12 and C13 compounds and extracted their corresponding bond length to a precision of 5 decimal places very clearly. That was the first experimental calculate. B will be calculated for, I can write, C12 oxygen, its corresponding B was calculated to be, the B for 12, carbon 12 will be carbon monoxide, okay? It will be 3.84235 centimeters. See, I have already 5 digits from the B value, so you can calculate the bone length very precisely and even the population by looking at the intensity. So that means carbon 13 has a natural abundance of how much? 1%, right? In the earth crust, right? You know that, right? This can be again rechecked by using micro spectroscopy very precisely, okay? Other than the carbon dating way that people use conventionally. Okay, so now I have to move to rigid rotor model. We can stop. It is boring to you. Shall I continue? What do you think? You have any questions up to this part? You have any questions? Anybody have any questions? They can of course ask. Otherwise, I can continue.
Yeah, please. I don't think you will get any questions. Maybe they, at the maximum, they send you through email. That's what we have been seeing.
Oh, okay. All right. So, shall I, Dr. Manoj?
Yeah, please.
Right?
Yeah, yes, I'm Dr. Manoj.
Yeah. Shall I continue with
please.
rotor model?
Yeah, sure.
Okay. So,
because the students are actually, they have these things in their syllabus, so they're always covering it up. I mean,
okay, very good. So, once again, in which stage they will be studying this? Like in the third year?
In the final year, yes.
In the final year. So, they have spectroscopy as one of the elective courses in final year.
Yes, it's just a part of the physical chemistry paper.
It's just part of physical chemistry. Okay, I hope it will be useful. So I will be continuing the same idea where I started with the rigid rotor. Now I have added something called non in front of rigid rotor. I was simply saying you that your bond length was fixed before. Now what will happen is your bond length is not anymore fixed. Okay, that means you take a simple situation. We started with hydrogen chloride, right? You take about any cases hydrogen fluoride. Any of these cases, if you write this particular bond, these are not a fixed bond anymore. And your energy, you already mentioned, it is 2p into j plus 1, right? Or this is, okay, this is not absolute energy, this is, j into j plus 1. So this changes. So what happened is that when you really measure hydrogen fluoride, there is a chance that if we increase, or there is, when the J value increases slowly from 0 to 1 to 2 to 3, etc., the corresponding B separation changes, right? I have actually, in the book of Bangalore has given a beautiful example, hydrogen fluoride case. I have to show you this hydrogen fluoride. So they calculated J is equal to 0, and then J is equal to 1, J is equal to 2, 3, 4, etc. What they have done is that for 0 to 1 transition, the B they obtained was 20.56. I am skipping all other digits, okay? You can, of course, get up to 5 digits, but I am skipping that. This is taken from a low resolution spectrometer. Then for J1 to 2, it is 20.48 centimeter millers. Okay, this is particularly for hydrogen fluoride. I'm going to show you an example to begin with. Okay, so for this is for transition between J1 to J2, and this is from J0 to J1. And for 2 to 3, it goes on like this. Okay, you see that it's become 20.43, and then this become 20.31 and so forth. So you see that there is a slight discrepancy or a change you will see in the system. Okay, why this change? You see, instead of we have to get 2p as a separation, always we assume that it was 2b. This is of course 2b, okay? But each of the state has separate 2b values. So there comes the concept of elasticity of the bond. Elasticity of the bond. I was telling you this idea of discus throw or shot put throw in an experiment. You slowly increase the angular velocity of the disc or the rotor, whatever you see that shot put. What happens is that as soon as it gets more and more energy, you can think about it's also elastic, it's stretching. So that makes it a bit more complicated than what you think, right? I'm initially fixed actually the bond. Now the bond is getting more and more elastic when I get more energy. So that is what exactly happening in hydrogen fluoride. Automatically this will come back to the idea of vibration spectroscopy. So in vibration spectroscopy, you consider omega, okay? Omega, which is called vibrational energy, which goes as 1 by 2 pi c into k by mu. I will cover this sometimes later. Okay, we'll cover this sometimes. So this is vibrational energy. C is the speed of light. K is the constant. Sorry, K is the force constant, and mu is the reduced mass. Okay, so these terms reduced mass, force constant come from the simple harmonic model of parabolic curve in energies distributed that we will see later. I can now write force constant K as equivalent to 4 pi square c square omega bar square right into mu. From this expression, right? This is a straightforward expression. So what happened is that due to this process we call the vibrational event which happened within the system. So now you think I was talking about rotation. Okay, rotation. Now you think I'm having a molecule, hydrogen fluoride is rotating with a given value of J. There is another process which happened, vibration. Okay, what means that this is where comes from the elasticity, right? So I think about like a simple harmonic oscillator. One atom is connected to the other atom by a spring. Okay, so now the short put throw become a bit more complicated if you connect the short puts, the string attaching to by a spring. So when you stretch it, you simply stretch, right? If the angular velocity increases, exactly what is happening. But keep in mind, in molecule, it is a bit more complicated. Okay, if I count the rotational time, if I say rotational time scale is happening in picosecond, okay, one rotation take place in 1 picosecond, assume approximately, whereas, okay, one vibration happens roughly 10 frames per second. Maybe roughly around, okay, 10 to sometimes 1 frame per second, maybe put it that way, will make a difference. There is a difference of roughly 10 power 2 to 10 power 3 times. This is what exactly happening in a molecule. Okay, when a molecule undergoing rotation, to complete one rotation on the principal axis or in plane of the screen for hydrogen fluoride, he will simply vibrate 100 times to 1000 times before it complete one rotation. So the vibration process is very fast. That's why you have all this fun, right? Chemical reactions, complexity of chemical reaction come into play. So I think you get the notion like how vibration is so important. So now I have very important to see what happens is that this is what happened dynamically, right? We are always seeing this classically, like I'm thinking the rotor is rotating, but you have attaching a spring to it to become more dynamic, then it moves. So for one rotation to complete, you have to think, it depends on the system, but it will be at least 100 times to 1,000 times, okay, before it make one rotation. So, I will show you this. So what is important here? I was telling you that B, you remember B is equal to H divided by 8 pi square I into C, right? That is B is inversely proportional to 1 by I. That is B is inversely proportional to 1 by R square. Am I correct? Right? So I can say straight away my rotational constant is inversely proportional to the bond length, the square of the bond length. Now you think, instead of having R, this term becomes something like R equilibrium. Or I can write some book in Bangal, it is written RE. That means my system can, instead of, I said, carbon-carbon bond length, I was fixed at 1.54 angstrom. Instead, it can occupy either 1.3 or 1.7. Okay, you see how complicated it will be. So that will lead to something called R equilibrium. That is the equilibrium bond distance. That is actually being defined later as the bond distance. Okay, so now you understand what Robert Hoffman said. Now with spectroscopically, you will define it as actually as equilibrium bond length, or it is actually after equilibration. So that is something very crucial. So there it comes the energy of the system. So energy of the system will be defined. I mean, I'll go to the next slide to show you this energy, which is again your previous expression of Ej, which contains P, comes out the 8 pi square I j into j plus 1 minus, you pardon me, I cannot able to show you how this has been defined. This is a very long derivation which include a lot of algebraic parameters. I am just skipping and instead I am writing. Okay, this will have j square into j plus 1 whole square term. Here this k is the one which is force constant, and I will write this expression by simply this way, Ej, because this is mostly interesting to me, by x by c, which is equivalent to b into j plus 1 minus d into j square into j plus 1 whole square. Okay, where d already defined, where d is equal to h cube divided by 32 by the power 4 I square r square k into c. Okay, so where this is called centrifugal distortion constant. Centrifugal distortion constant. So I can have all other terms, but I take only the first term, which is a d. Okay, so you can have the corresponding, this is the square term. I can have cubic and quadratic terms, which is goes on like this. Okay, you can have cubic term and quadratic terms and etc. etc. But keep in mind that when we do, b can occupy some value. I was just mentioning, you see the b was some 3.8, right? We mentioned for 3.8, some centimeter verse, right? So what will happen? Normally d will have roughly 10 power 3 times lower value. I mean, this is approximation, okay? Approximately value than b. That means b will be a very small quantity. Sorry, d will be a very small quantity. Okay, so you can, if you want to use it in your approximation, you can still take d as 0 and then simply avoid it. Or if you really want, you can take it and calculate it. So in vibrational spectroscopy, you normally don't use it, skip it. Okay, so because D is sometimes negligible, so when we do rotational spectrum of raw vibrational spectrum of a molecule like hydrogen chloride and so forth, we simply skip D, we take V equal to B effective, which is equivalent to B minus D. Okay, so this is what happens in reality when you do using FTIR. Okay, infrared, but in real micro, you can easily take the value D and get much accurately the data. Okay, so there in the book of Barnwell, there is a lot of discussion given. So I was just telling that vibrational states are happening. Normally, vibrational energy omega bar I represent happen in 10 power 3 centimeter inverse. Okay, B normally occurs roughly around 10 centimeter inverse, and D will have a value of roughly 10 power minus 3 centimeter inverse. This make you easier to understand these energies, right? These constants at least. I hope that it is clear to you. And non-rigid water, it will have a skew energy compared to the rigid water, in which it simply deviate higher values of J. Okay, so I think that is enough for today. I think otherwise it will be too boring for us to go further. I can give you an example. Maybe there is something called Carser relation. So I don't know whether that we will discuss maybe in the next class very quickly. The Carser formula will connect B and D. You will get the vibration energy. So the relation is something called omega square is equal to 4BQ by DQ. I think something like that. 4BQ by D. Okay. This is the relation. So if you know your B and D, you can calculate your omega bar. Okay. That is your vibrational states, and this is how this is connected. You will see this also some correlation. This is called Kratzer relation. This is actually, that's where it's coming from. Again, the historic appearance of vibrational spectroscopy in the beginning. So you have got the vibration frequency and the B from raw vibrations, and you can calculate back your D set of the distortion. Okay. So we covered up to non-rigid water. I think I will continue this discussion for vibrational spectroscopy tomorrow. Okay, that may be more easier than going into other topics. I can take any questions you have. I have a meeting at 5, so I will stop maybe now, and maybe if anybody have a quick comment or a question, I can take it.
Yes.
Dr. Manas, yeah. Otherwise, it's too boring, right? We'll start vibration spectroscopy tomorrow. I will start single harmonic oscillator model.
Yeah,
that's
sure.
More easier.
Yeah, that should be good.
Anyone want to ask? I mean, otherwise, you please write me. I'll be happy to share information.
Yeah, students. Yeah.
And,
Dr. Jino, I have a question. How much does this, I mean, not to the subject anything, but how much does this rotational spectroscopy instrument cost? I have not seen one.
okay.
Cost-wise.
For micro spectrometers, normally they go up to 100 Gauss numbers, or sometimes I don't know what exactly. I also have Node 1 in my lab, but normally we use bolometer for that purpose. They go up to 100 Gauss numbers, if I am correct.
Okay.
Maximum.
Meaning, what is the cost actually? What is the cost? I have no idea. Sorry, okay. I have no idea. Immediate, if you are more interested on that, immediate contact. Yeah. Just curious because we don't see it most often.
You don't see it regularly, yes.
Yeah.
So we have also, there in IISER, there is in the IPC department, they have a vibrational, a Fourier transform FT microspectrometer available.
Okay.
I know. Professor Arunan has it. A couple of others also have it, like in TFR and some other places. It is actually a very good tool. I mean, this entire classical relation you can try to prove with any of the gas phase. So the limitation is the gas phase. You can only deal with gas phase. That's all difficulty. So real system won't really work, but this is actually give a prototype how a molecule bond look like. That's very fundamental in the aspects.
Yeah.
Right. Okay. Fine. So we will then see tomorrow.
Yeah. Probably we'll meet exactly at 3:30.
There I will cover. I will start with the vibrational spectroscopy of a single harmonic oscillator model. That will again help you to, maybe this will help to understand how the model is vibrating. Then we'll go to the later part.
Sure, sure.
All right. Thank you. Thank you very much.
And Dr. Jino, Dr. Ram Shastri is my friend actually.
Oh, great. Okay. Very nice. Very nice. I will tell your regards to him. Yeah. Sure.
Okay, bye, Professor Jino. We'll meet tomorrow, 3:30.
We'll definitely, we'll try to meet. Yeah. So tomorrow at 3:30. Yeah. Thank you very much.
Yeah. Thank you.
Bye.
Yeah.
Take care.
Bye.